Okay, so we are going to be doing chemical kinetics today. First of all, chemical kinetics. Do you guys know what do you mean by kinetics? What does kinetics refer to?
Motion.
Motion, okay. Motion में क्या? Have you guys dealt with this before? Kinetics, matlab
Kinetic energy.
that relates to what?
Movement of particles.
Movement. And like a primary property when it comes to movement is what? Velocity, speed. Like that's what you associate, right? So when we talk about chemical kinetics, pretty much the same thing. So we're going to be dealing with the speed of the reactions. Okay. So physical chemistries are all to do with the physics behind the reactions, like how do you control the reactions. Grade 11 thermodynamics may you had spontaneity and enthalpy and energy associated with the reactions, right? Entropy and enthalpy dono mila ke you can figure out whether a reaction will take place or not. So usse you got to know the feasibility of the reactions, whether something is feasible or not in the first place. Can you do it? Do you need to spend a lot of energy in creating the correct temperature, pressure for that reaction to happen? Or is it spontaneous? Then equilibrium mein, you got to know, like we looked at the extent of the reaction. So where is the equilibrium? Where is the reaction stopping at? After 90% of the yield, after 25% of the yield, after like 50% of the yield? How far is the reaction going to go? How much product am I going to get out of it before the reverse reaction kicks in? Now, the third aspect, like if you want to control reactions, if you want to use it to manufacture products, you need to know like the speed of the reaction as well. And this is what we'll be looking at in this chapter. So how fast is the reaction? Now, every reaction is not instantaneous. How long does rusting of iron take place? Like if you have a piece of iron, how much time does it take for its oxidation? Rust hone mein.
Months.
Months,
Yeah.
right? If that is the reaction we want to emulate, like we don't want a reaction that takes years and months to happen, right? We want something faster. So you have a rough idea, like based on experience, how fast like different reactions are. So you have some very fast reactions. So all the ionic reactions come under this category. So acid base neutralization. अगर कुछ precipitation हो रहा है, do you guys remember 10th में we had studied this lead iodide का this thing, this sort of a reaction. So as soon as you drop in lead nitrate and potassium iodide, you have this forming instantaneously, right? So all your displacement reactions, all these sort of ionic reactions, okay, they happen instantaneously. They are very fast reactions. Okay. And then you have like extremely slow reactions. Very slow reactions are rusting of iron, formation of diamond or graphite or coal from like plant matter, animal matter. That takes like millions of years. So you have extremely slow reactions that take place over a range of like days and months and years. Iron. Formation of coal is another one. Formation of carbon, be it coal, diamond, graphite, jo bhi hai, takes a long time. And then you have moderate reactions, like moderately fast reactions. So this falls somewhere between very, like it's not instantaneous, like very fast reactions like your ionic reactions, but it's not extremely slow. So it takes place over the range of a few hours or so. These are something that you can control. So you can just control it by changing the temperature conditions, maybe pressure conditions, to make it slightly quicker and make it more useful for your yield, jo bhi hai. Okay. So we will be looking at, like, at least in this chapter, when we talk about chemical kinetics, we'll be looking at a lot of moderate reactions, general ones. Very fast, you can't do anything about it, because ionic, especially if you have acid bases salts, as soon as you put them into water, they dissociate into ions, and then once the positive and negative comes into contact, you have your product. Slow, I mean, yeah, you can apply some conditions, at least you can apply the calculations to really slow reactions. But when we're looking at studying and figuring out and looking at the trends and all, yeah, it's a lot of studies we done on moderate reactions. We're looking at those right now. Okay. And as an overview of the chapter, in this chapter, we look at rate of a chemical reaction. What do you mean by rate? How do you express rate, like formula, units, that sort of a thing?
Ma'am, could
Yeah.
you go to the previous one?
Yeah. This is just like introduction. See, examples, okay, you can just improve this. Ionic reactions, you can say. So acid base, like neutralization, double displacement, these all happen quickly.
Done.
Yeah. So I was saying, yeah, this chapter, first we look at what is the rate of reaction, like the expression, units, formula, all of that. Then we look at factors affecting the rate. So just like how we studied solutions, what all will affect rate of a reaction? So temperature, concentration of reactants, products, all of that stuff, nature of the reaction itself, order, molecularity. Then we look at integrated rate reactions. Okay, so specific. So depending on the rate of the reaction, we have different types of reactions. You have first order reactions, zero order reactions. We'll look at specific ones like that. And finally, the collision theory behind how chemical reactions happen. Yeah. So this is like a it's okay, not very short, but it's not like intense. This is a nice chapter. It's a small chapter. You can easily, the concepts are not very intense or heavy. You'll have numericals. That's something that you have to get through, but at least it's not like, yeah, one of the lighter chapters, physical chemistry.
Having numericals is the problem.
But that's the only thing you need to focus on. It's last year thermodynamics, equilibrium were a little intense. They were completely new concepts and all. This is not like that. It's much lighter. It's more heavier on the mathematics side than the concept side. Okay. Okay. So we'll start with rate of a chemical reaction. So if you want to measure the rate or a speed of chemical reaction, you can usually express it in terms of, like, in two ways. One, you can check how quickly the reactants are being used up, or you can check how quickly the product is being formed. Okay. So you can calculate rate in terms of the decrease in the concentration of reactants, or you can track it based on the increase in the concentration of products. So anyone. Okay, so when do you use what? Like all of that depends on your like how you're conducting the experiment, what reactants are there, what products are there, and where you're measuring, at what point you're measuring. But yeah, either way. So mathematically, if you were to see, if you have a reactant giving rise to a product, hypothetical reaction. So let's say when you started off the reaction at T equal to T1, let's say the concentration is, let me just move this.
Ma'am,
Yeah.
I have a silly doubt, but like, won't decrease in concentration of reactants mean like increase in concentration of products?
Yeah. That's
Like,
not
both are the
silly
same
at all.
thing. They both are the same thing, right?
Yeah, that's why you can use anyone. Won't make a difference.
Okay.
Yeah. Okay, so at T equal to T1, let's say concentration of reactant is R1 and product P1 itna form hua. And after some time, when you checked at T2, concentration became R2 and product became P2. Then we are looking at either decrease in concentration or increase in the concentration, right? So the change in the concentration of reactant will be how much? How do you usually measure change?
Current minus original.
Like final minus initial, current minus original. So यहाँ पे for reactants, what will be the expression?
Final concentration of reactants minus initial concentration of reactants.
हाँ, तो R1, R2 assume किया ना?
Minus
R2 minus
R1. Okay. So, but because this is decreasing, usually there's like a minus. So we'll look at it in the next step. Usually you apply a minus to indicate that it's decreasing, negative of this thing. Okay. Then, or change in the concentration of product, similarly, same thing. P2 minus P1. Okay. So now, in order to calculate the rate of a reaction, so rate of decrease, so how quickly the reactant is disappearing. So rate of disappearance of reactants will be equal to,
Why the minus sign before a delta R?
because it's decreasing. So we are calculating kitna change hua na. So if you do final minus initial, as the reaction goes on, R2 will be less than R1. So rate will you represent it in terms of minus. So when it comes to rate, now how do you calculate the rate of disappearance?
Divided by the change divided by the original process.
No, that won't give
Oh,
you
sorry, that's the
relative change kitna hua. So whenever we talk about rate, like you have come across this concept in physics also, right? Lots of times. So whenever you're looking at rate, what's
divided by T2 minus
Divided time.
time is correct. So the rate of disappearance of reactant will be minus delta R upon delta T, which is T2 minus T1. Or let's write it as delta T. Used to it. So note it down here when we say delta T change in time will be T2 minus T1. It's very, very like all of these calculations, you can draw parallels with, motion K calculations, like other things that you measure with respect to time. So And same thing, if you want to look at it with respect to products, then you'll get rate of appearance of products, which will be equal to change in concentration of product per unit time. Okay. So these quantities, like if you're looking at it over a broad range of time, since you're using delta T, this would come under average rate. If you guys remember mechanics mein, you had concepts of average velocity versus instantaneous velocity, right? So average velocity, you basically, it's a very broad thing. Okay, 1 hour mein I traveled so much, then on an average my speed is so much. So this is also mirrors that same thing. You're measuring it over a large time and then seeing ki kitna change hua in terms of concentration of reactants and or the concentration of products. So when you measure the rate in this way by subtracting, like figuring out over a range of time period, what you get is average rate. Okay, clear? So how would you measure instantaneous rate of a reaction, Fir?
When T is tending to 0.
Yes. So mathematically, how would you put it?
D by
Like D whatever by dt.
Yeah. So
if
instantaneous
it's
rate,
reactance dr by dt or something.
yes, minus dr by dt, which will be equal to positive of dp by dt. Okay. But obviously, experimentally, it's not possible to measure the instantaneous rate. Because at 1 second, you can measure what is the concentration. You can't see the change in concentration. So experimentally,
Yes,
hmm?
sorry, in the previous one for rate of appearance of product, it was positive, right?
Positive, yeah. इसलिए मैंने okay, just put a plus here. Yeah. So
No,
this
not like that, but
reduce हो रहा है इसलिए negative. This will be positive only. See. So experimentally, again, if we are plot a graph of what is the variation in the change of in the concentration of reactants and in the concentration of products. So this is the sort of graph that has been observed. So दोनों के case में it's a exponential curve. It's not a linear curve like most of the cases. Again, it depends from reaction to reaction. But in general, okay, let's first graph, if you're talking about it in terms of reactants, over time it reduces. So this is the kind of shape that you get. And the products ka thing is going to mirror it, except it's going to increase. Like agar ye exponential curve ho raha hai, this also will be a logarithmic curve. So product is going to be like this. Okay. So yeah, so in terms of like rate calculations, same thing. So if you're looking at average rate, you're going to be looking at a slope bit like between 2 points. So you see at t equal to 1 kitna hai, t equal to 2 kitna hai, and subtract r2 minus r1. And if you want to find the instantaneous rate, you calculate it based on slope of the curve. So at any time t, if you want the instantaneous rate, it's going to be slope of the graph. Okay. So I'll put it in different colors. So if you're looking at average rate, so this is T1. Let's say this is at T2. T1 pe concentration happens to be this much. Let's say this is R1. And T2 pe the concentration has reduced to this much. So this will be R2. So R av is going to be slope of this line. Average rate will be minus delta R upon delta T. And if you want to calculate the instantaneous rate, let's say at time t over here, so it's going to be slope to this graph. R instant will be minus dr by dt. So even in the case of product,
How did you get R instant? I didn't understand.
How
Like
did
the
it-
line, the yellow line. Why did you?
so like dr by dt. So whenever you do one step of differentiation, you're calculating slope to the curve. Okay. So over a range, slope कैसे calculate करना है? मतलब you subtract y2 minus y1 upon x2 minus x1. But if you want to calculate the slope at a particular point, you differentiate it once. So that's why it's dr by dt. Okay. So same thing here also. Like, do you guys want to draw this or write this on your own? So let's say T1.
Miss, that is our average, right? Like average rate, right?
Our AV is our average, our INT is our instant. This is P2. So average will be the line between this point and this point. So we calculate the slope to the curve, y2 minus y1 wala thing. So our average will be delta P upon delta T, and instant rate calculate करना है at this point T मतलब it'll be the slope tangent to this curve. So at this point, our instant will be like dp by dt. Okay. So here we have expressions. Rate equal to, so difference in the concentration of reactants upon dt, which is also equal to rate of disappearance will be equal to the rate of appearance of products. So based on this, can you figure out what would be the unit of rate of reaction? So how do you measure?
Concentration by time.
By time.
Usually, yeah. So generally, it would be units of concentration. So if you're doing it in solution, it is going to be mole per liter per second. And if the reactants and products are gaseous, you calculate concentration in terms of partial pressure. So that's going to be atmosphere per second. So either concentration per time or pressure per time, atmospheres or pascals or bar, however you're calculating.
Why pressure?
Because when the reactants and products are gases, like for example, if you're calculating rate for production of ammonia, so nitrogen, hydrogen, and ammonia, all of them are gases, right? When the reaction takes place. So usme mole per liter does not make sense. Like when you have gases, you measure it in terms of their pressure. But if you
Ma'am, that is
Hmm?
P average, right? For the and P instantaneous.
instantaneous,
P, right? Not R.
no, R means rate. Small r refers to rate. That's how rate.
Oh,
No, ma'am.
okay.
Uh,
Oh, okay. Even in the one for like delta P1 is also for rate,
yeah,
like the R.
yeah. So if you're referring to rate reactants or products, it's always capital R, capital P, and always use these square brackets here to show the concentration. Okay. So small r, this represents the rate, R av R inst. So this is for like a very simple reaction where we assumed, okay, one reactant here that is turning or changing into a single product. So now we look at like specific cases, specific reactions where there may be multiple reactants or multiple products or both. So once you guys have finished noting the graph and everything, let me know. We'll do that. Whereas and Kaveri is finished noting. Yeah. Okay, Sia, Arya, Sanskriti. Let me know when you finish.
Ma'am, I'm done.
Okay. Sia done? No, okay.
That is ATM or Pascal per second.
Yeah, it like just if you want, you can note it down as a generalized thing. So unit of pressure if you have gaseous reactants, and यहाँ पे it will be unit of concentration if the reactions are done in solutions. So this is for gases. And this is when it's a solution. Okay, so when it's not a very simple reaction, so if there are stoichiometric coefficients, multiple reactants, multiple molecules of reactants, multiple molecules of products. So for example, let's take decomposition of HI gas. So 2HI decomposes into H2 plus I2. So whenever you measure the rate of appearance or disappearance, यहाँ पे in order for one molecule of hydrogen or one molecule of iodine to appear in general, this reaction requires a minimum of 2 molecules of HI to go in, right? So these sort of cases, then the rate equation modifies too. If you're looking at it in terms of disappearance of reactants, because 2 molecules of HI are going in, and you need 2 molecules. Every time you calculate rate, so one thing is that every time you calculate rate, you calculate it in terms of like 1 mole of the reactants. So in this case, if you're calculating it in terms of HI, you need to divide this whole equation by 2. So the rate of disappearance of HI, this becomes minus half into concentration of HI upon change in time, which will be equal to the rate of change of like appearance of H2, the rate of per unit time, which will be equal to the rate of appearance of I2 per unit time.
Why divide by 2?
Because you always measure it per mole of whatever substance you're looking at, whether it's reactant or product. So you need like for the reaction to take place, you need 2 moles of HI to produce minimum of 1 mole of H2 and 1 mole of I2, right? So if you calculate as it is, everything is like, at least in terms of reactant, if you're looking at the disappearance of HI, everything will be multiplied by a factor of 2. So that's why you have to divide it by whatever is the stoichiometric coefficient. Yahan pe 2 is the stoichiometric coefficient, so you divide it by 2.
I have a silly question, but since H2 and I2 are both part of the products, why
Mhm.
don't we add them when we equate the rate of change of the reactants and the products? Why do we equate them? Like, why are they?
Because
They don't add
once
up to me.
because once we like once the reaction happens, if you're measuring the rate of how quickly H2 is being formed, automatically matlab I2 also will be formed. So it will become redundant if you add both of them.
Oh, yeah.
Yeah.
True. But
So you like every time you have a rate equation expression, you take any one of them at a time. Then, so you guys wanna like what would be the expression, the rate expression for